Well, hello, everybody. Special welcome to the committee. Thanks for taking the time to already read the system thoroughly, and thanks to my family for making the trip. We'll be talking today about learned data augmentation for bias correction. So what's the problem here? Machine learning works by extracting patterns from data. And this talk will be concerned with cases where we are missing data in specific ways. For example, an algorithm here learning to read brain scans to predict whether a brain is healthy or at risk of developing a tumor. If we train such an algorithm on data, say here from DTU, it would likely see more male brains than female brains during training. And as a consequence, we'd expect it to work a lot better than on men than women when deployed in the wild. Indeed, in the last couple of years, we've seen algorithms dramatically fail in this way. So, for example, we've seen racist algorithms in the criminal justice system, sexist search engines, or hiring tools as some examples. The underlying issue here is that data bias translates into model bias. And this is surely an ethical problem, but not having enough data is also a technical problem that we've studied quite well within machine learning. And we'll try to capitalize on this existing work on data augmentation in this talk. So let's start with that. The setting is something like this. I have a data set consisting of some inputs X and some labels Y. I have ND of such pairs, and I'm trying to fit a function that's parameterized by some weights W, such as Fx is roughly Y, for all of my data points. We'll also sometimes consider this probabilistic formulation on the right, where we just try to maximize the likelihood of the label given the image or the input. In neural networks, though, this W can be millions or billions of parameters, and ND might be orders of magnitude smaller. So we will see overfitting, poor generalization, these sort of things. And the formulation that we have here on the slide, it suggests two strategies to fix this problem. So either we could reduce the expressivity of the model, so making W smaller, or, well, we could make ND bigger. And the second strategy, increasing the number of data points, is what data augmentation is concerned with. Just a note on data before we move on. So we usually assume data to be IID and specifically independent, so that the PFD factorize it like this. But this assumption is violated in standard data augmentation, as we will see in a moment. So what do I mean when I say standard data augmentation? The idea is to generate new data points from existing ones using simple modifications. So for example, scaling, rotation, or color augmentation. This is a long-standing engineering practice and one of the tricks really that made deep learning work in the first place. So Krasivsky and others in their seminal work write, without data augmentation, they would have been forced to use much smaller networks. But there are two problems with this approach. First, as I said before, there's these independence assumptions that we're usually making, and those are violated in standard data augmentation because, well, if I'm generating a new data point from an existing one, surely these are not independent anymore. Secondly, we're making some strong modeling assumptions here. So essentially, if we use data augmentation, we make some assumptions about invariance, right? So here, for example, the function I'm learning should map the original brain to the same value as the color augmented brain. And in general, we can make such assumptions quite well with natural images in the wild. But already here in this brain example, it's a little bit unclear. Can I simply mess with the color scheme of this MRI scan and not change the information? So it can be quite tricky to say what are reasonable modeling assumptions here. In this technical part of the talk, we'll try to fix those two problems, and then we'll link it back to the bias problem after. So just to make it explicit, so we've already seen the problem statement. Underrepresented groups in the training data experience poor model performance. In the technical part on data augmentation and invariances, we will consider ways to generate synthetic data. This is papers 1 and 2. We'll then investigate whether the synthetic data can be used for bias correction, so to close this gap in accuracy between groups. And to do that, it'll turn out that we'll need to take a closer look at fairness modeling as a whole to evaluate whether we really succeeded. Then we'll wrap up. Okay, so how to fix the two problems with standard data augmentation? I remind you what those were. First, the IID assumption is violated. And secondly, how to find good transformations, good invariances. Let's start with the first one. So we have seen that data points are generated from each other, right? Like transforming one, a new one, and those are no longer independent. So instead of viewing the new data points as independent samples, we suggest to take a probabilistic viewpoint and essentially view them as samples from an augmentation distribution, which we marginalize. So we model the joint of some labels and transformations and marginalize the transformations to arrive at our data augmentation model. The second problem, well, what are good augmentation distributions? What's the optimal P of t given x? The naive sort of ML way to do this would be to parameterize this distribution with some weights, right? And then maximize the likelihood with respect to the weights. However, this actually doesn't work. Data augmentation acts as a regularizer, and regularization does not actually help to improve the fit on the training data, as you know. So if we here train models with different degrees of augmentation, blue is no augmentation, green is too much, red is maybe just right. We see on the right plot here that the red model has the lowest test loss. So this is the mean squared error. Red is on the test set. But on the training data, using no augmentation at all actually gives us the best likelihood. So if we only use the training loss to find this parameter, we would simply learn to not augment at all. So the augmentation distribution would collapse, and so we cannot use this approach for learning data augmentation. However, it's not entirely hopeless, because if we take this idea seriously of viewing data augmentation as regularization, then we can think of learning data augmentation as a model selection problem. And we know that in the Bayesian paradigm, we can do this automatically by maximizing the marginal likelihood. So we marginalize the function weights themselves, and then we optimize with respect to some hyperparameters theta. I'll remind you why this works. So consider this plot I have on the x-axis, all possible data sets. And on the y-axis, I have the marginal likelihood for different models. Here, blue, this is a very simple model. It can explain only kind of prototypical data sets around the mean, but those quite well. In red, this is a model of intermediate complexity, so it can explain a few more data sets, but then those it doesn't explain as well. And this is because, well, the marginal likelihood is still a density, so it needs to integrate to one. So if I assign mass to lots of different data sets, I can only assign less mass to any individual data set. Similarly, for a very complex model, well, it can now explain a lot of different data sets, but assigns very little probability to each of them. And this is why for any individual data set, Y0 here, the marginal likelihood will select exactly this model that has just the right amount of complexity. And let me reiterate, why is that useful? Well, because we will consider our data augmentation parameters to be a subset of these theta parameters. So we can now maximize with respect to the WA. Before we'll really exploit this idea, I'll just give you some background. So what does this WA actually mean? We'll often look at affine transformations because they're differentiable. That means that our transformations such as rotation, scale in X and Y, shearing and translation. And so WA is simply the maximum amount of rotation and shearing and translation and so on. So it's only 14 parameters actually in this first piece of work. And then you see an example in the bottom. This is rotated MNIST, where we learn that transformations are useful where we are fully rotational invariant. So W or alpha min, alpha max is plus minus pi, but all the other parameters are 0. So we only learn rotational invariance. We'll see that in a moment. A second piece of background we'll need is a class of model called Gaussian processes. Recall that we need to estimate this marginal likelihood, so integral over all model weights, but also remember that I said in the beginning that this can be really millions or billions of weights in a neural network. So this quantity is going to be very intractable for neural networks. There's some work done in Bayesian neural networks, of course, but it's still very much an open research problem. So instead, what we did is we considered a different class of models, Gaussian processes, for which this quantity, the marginal likelihood, is tractable. We also know from the literature that with this class of models, one can actually learn data augmentation or invariance. So this is Van der Wilk and others' 2018 work. They construct an invariant GPF from a non-invariant function G by marginalizing the augmentation distribution. So very much as we suggest. The kernel is then also simply the original kernel marginalized in both inputs over this augmentation distribution. And again, this kernel looks pretty intractable, right? But what Van der Wilk and others do is they introduce a sample-based elbow for Gaussian likelihood. And with this approximation, they can indeed learn invariances. So here on the bottom right, we see a data set where the ground truth is 90 degrees rotations, and they can indeed recover these rotations, so they correctly learn the invariances. So this is good news. Learning data augmentation is possible, at least it's possible in GPs. Does it scale to neural networks, though? This is the question that paper 1 tries to answer. This paper, last layer marginal likelihood for invariance learning, is published in AI Stats this year. Okay, I remind you, the challenge is to estimate the marginal likelihood for neural networks. We can't do that for the full model currently, but the idea is maybe a Bayesian last layer could be sufficient. So maybe this is an approach called, or one of the ways to implement this at least, is deep kernel learning. For our model will be an invariant deep kernel GP, and that means the following. So deep kernel learning is pretty much, you take a neural network, you cut off the last layer, fully connected, and you replace it with a GP, so with a Bayesian last layer. We combine that idea with the invariant GP from Van der Wilk and others. So the full model is something like this. I pass an input, I span this augmentation distribution where sampling usually, pass all of the samples through the neural network, aggregate in the last layer, and then make my predictions. To perform inference in this model, we need to estimate a bunch of parameters, of course. So there's the GP hyperparameters, the variational parameters, and then importantly for us here, this invariance parameters WA, and of course the neural networks parameters that we just introduced. Usually in deep kernel learning, you would train jointly the GP parameters and those WC parameters. However, in our case, it leads to overfitting. It's also not too surprising. It's quite well documented in the literature. And for us, this means the following. So if I have 2 train images from the same class, but at different orientations, if I train in the classic deep kernel learning way, those will be mapped to embeddings that are pretty much the same. So these blue embeddings really don't have a lot of signal to learn invariance from. On the other hand, if I train a regular neural network, I see that these within class features, they're much more diverse. So from these features, I actually have some hope that I can learn invariances. And yeah, this generalizes across classes. Is not because something is wrong with my twos. This this problem directly kind of suggests a solution, though. We could kind of iteratively update the WC and the GP parameters. So if I just start with these red features, I can then learn my invariances and go back and forth between the two. And this is indeed what we do in paper 1. There's the second problem, though. So in the Van der Wilk paper, they use an elbow that's specifically designed for Gaussian likelihoods because it uses a closed form integral. But of course, we're looking at classification problems here. So this is a likelihood misspecification. This means for us that there's even worse overfitting and collapsing augmentation distributions. Here in this plot, we see the likelihood variance parameter on the left pretty much goes to 0, and so does the learned angle on the right. Now, one thing we can do is we can simply fix the likelihood variance parameter like we did here in blue. Then we can actually learn invariances here on the right. So that's great. We kind of still stuck with a hyperparameter to tune now. Now it's not the invariance parameters, but it's this likelihood parameter, right? So ideally we would not use this hack. And so we introduce a more proper principal solution, which is a lower bound to the elbow, which can handle arbitrary log concave likelihoods like the softmax. And essentially we're just sampling the top equation in a kind of smart way and use Jensen's to get the new bound. As a result, we do learn invariances. So here again on rotated MNIST, we learn to be fully rotationally invariant. This is the solid lines for both likelihoods. And we learn almost no translational invariance in the dashed line, which makes total sense. So this is exactly what we would expect looking at these pictures. These are not translated, but rotated. Those invariances also translate into better downstream performance. The invariant deep model outperforms both shallow models and also deep non-invariant models and produces state-of-the-art results. So yes, learning data augmentation is also possible in neural network-like models. I write here with limitations, and I think the biggest one is certainly this iterative training, because that kind of means that at first we need to train a model without data augmentation, and that's just not possible for all architectures, especially deeper architectures kind of depend on the data augmentation already in this first pre-training step. And also regarding things like computations is really quite complicated, this first approach. So maybe there's a simpler way to do this. The simpler way of doing it is explored in paper 2, probabilistic spatial transformer networks, which is published in UAI this year. And the idea is essentially to pose normalize in order to get invariances. So I remind you, so far we have marginalized transformations like here in the top to obtain invariance. But alternatively, we could optimize the transformation. So find one single transformation that's useful, and then just use this kind of pose normalized image. This is implemented in spatial transformer networks, and I'll just show you what pose normalization means. So I have an input, and the modeling assumption is that there's one transformation that maps this input to an easier version that I can then perform my downstream task on. This idea is, it's quite influential, and I think it's a beautiful idea. But we also know that these SDNs, they're quite brittle and hard to train, and also it's not necessarily well defined. What do we mean by the optimal transformation? Like one could easily say that there might be several orientations at which I can classify the image just fine. So as a consequence, we propose a probabilistic extension here in the bottom. And we again use this idea of marginalizing transformations here just across or around the mean. Interestingly, evaluating this integral with Monte Carlo methods, this corresponds to kind of trying multiple transformations and again, some type of data augmentation essentially, because, well, we draw samples from this augmentation distribution. And indeed, the PSDN improves localization, accuracy, and calibration over its deterministic counterpart. I'll just show you this one experiment where we aim to pose normalized MNIST from class labels. So that means that we train a classifier on regular MNIST, then we perturb the data, rotate it, and then we train a PSDN, which needs to untransform the image so that the downstream task can be performed well. It does so successfully. So You see here in this middle plot, the true rotational angle and the recovered one, they're pretty much on this identity line, so this worked. And on the right, you see that the PSTN even worked a little bit better as expected than the deterministic STN. The localization error is smaller and the classification accuracy is, as a consequence, higher. For limitations, we find that the PSTN inherits some of the limitations of its deterministic counterparts. So there's this failure mode in STNs where if I have a very deep classifier downstream model, it can be so high capacity that it can just learn to do the task no matter the orientation. So it can just learn to classify these rotated images directly without transforming them first. And so here on this plot on the right, we see that models with more layers, they have little transformation variance here, just meaning that they always predict the identity. So the classifier does all the work and the localizer just predicts the identity everywhere, which is of course not what we want. The PSTN does slightly better here for these models of intermediate size. It can kind of alleviate this problem, but eventually we face the same failure mode. So which model to choose then? Excellent question by the committee. I'll try to walk you through some differences. So the idea is different, right? The invariant deep kernel GP tries to be invariant via augmentation. PSTN tries to be invariant via pose normalization. Mathematically, the biggest difference is in the variational expectation. The invariant deep kernel GP marginalizes F and also marginalizes the augmentations. And the PSTN optimizes F and marginalizes the augmentation. The invariant deep kernel GP learns a global augmentation distribution. The PSTN learns one per image. And in the limit of infinite data, the variance of the augmentation distribution tends to the true data variance for the invariant deep kernel GP and to 0 for the PSTN, because we get more and more certain about what's the optimal transformation here. Which is better? I think the per augmentation distribution can be quite useful because you could easily imagine a case where some classes have other invariances than others. So in MNIST, I can probably rotate 1s all the way, but if I rotate 6 and 9s, I introduce some ambiguity. So it could be useful to have different augmentations per image, or at least per group of images. On the other hand, the invariant deep kernel GP implies a more direct generative model. So if I have a full model of this variance in the data, I can use that model to do downstream tasks, which we already know is really helpful, data augmentation. That's what we're trying to do. This is, of course, due to this principled underlying model of the Bayesian model selection. So that's nice. It's also really expensive to do anything. So at this point, the PSTN is a lot more scalable. Yes. Both models face some computational limitations. So in the invariant deep kernel GP, the marginal likelihood approximations are currently pretty much missing for full Bayesian neural networks. At least they're not good enough to do model selection with them. The PSTN, the hardest part, I would say, is to estimate this mean, or this STN, the deterministic part of the model. And this is only partly alleviated by the probabilistic formulation, as we've seen earlier. Again, due to this very principled underlying model in the invariant deep kernel GP, it seems to me that there's a clearer way forward. For example, Imma and others suggest using Laplace approximations, which seem promising for more robust marginal likelihood estimates in neural networks. Okay, we will conclude the technical part here and return to the bias problem. So, can we use this data augmentation scheme for bias correction? We do a case study on this. So we'll look at the Celebrity A dataset. This is a dataset consisting of images of, well, celebrities. These are labeled with these 40 attributes, 2 of which are attractive and young. And we will build a classifier to predict the attractive label. And we'll test whether the classifier is biased. And you maybe think this is a little bit ridiculous and we shouldn't automate it. And I would tend to agree with you. We have chosen this partly out of necessity because it's not so easy to come by suitable fairness data sets for our setup in the computer vision domain. And I would also just like to say that it's actually a reality. So the popular dating app Tinder has used algorithms to score people's attractiveness in order to match users in the past. We start out by measuring whether there's any bias in the data. To do so, of course, we need some criteria. We use two very well-known metrics from the fairness literature. One is demographic parity, which measures whether the probability of being attractive is the same for the old people and for the young people. And then there's equality of opportunity, where we additionally condition on the ground truth label. So essentially, we check whether the errors are the same across the groups. And as we expected, there is no demographic parity in the data, so the probability of being labeled attractive is higher for the young population than the old population. Not too surprising, probably. And the hypothesis is that data bias leads to model bias. So let's check that next. To do so, we train a simple neural network, which achieves about 80% test accuracy on the task. As expected, the fairness metrics aren't satisfied. So indeed, the model has inherited the data bias. So we measure for demographic parity, we measure the people predicted attractive in the young and the old population, and then we just divide the numbers to aggregate into one score. Same for equality of opportunity. And we see that for a fair model, these would be 1, they're not 1, so there's a model bias. Question is whether we can get rid of this bias. We compare 3 strategies here. First is adjusting thresholds. So our model for each of these inputs in the bottom, it essentially gives you a probability that this person is attractive. Normally we threshold this probability at 0.5 and then assign labels. Oh, if it's bigger than 0.5, yes, attractive, otherwise no. And a very simple debiasing strategy suggested in the literature is just to essentially lower the threshold for your underrepresented group, and then you automatically get more people labeled attractive. The second strategy is naive upsampling. So here we just take these underrepresented groups, here the people that are both young and attractive, and we just make copies of them. And then lastly, our strategy, here we do the same, but we also augment the people that we upsample. And let's just look at our model to see whether it works. It does work. So as we increase these ratios of the underrepresented group, the demographic parity ratio gets better and better. Also, the equality of opportunity ratio. And maybe I should also point out in blue, we see that the accuracy drops, which is not so surprising because I'm kind of screwing with the underlying distribution of my data, right? So that's great, but is this better than the other strategies? I think we should ask questions like, can the desired level of fairness be achieved at all under all of these 3 methods? And then how much do we lose in accuracy? In our case study, it turns out that it's actually only thresholding that can even achieve demographic parity. Here in the top for equality of opportunity, all 3 methods can, but for demographic parity, only the thresholding method can. It's also thresholding which produces the smallest loss in accuracy to get to the desired level of fairness. However, and this is a big however, thresholding requires test time access to the protected attribute. This is a problem because A, we might not have that access, and also it's illegal under anti-discrimination law in a lot of contexts to use these protected attributes. That's why they're called protected in the first place. Okay, so can we use data augmentation for bias correction? Yes, but is it the best strategy? It depends, right? So it kind of depends on, will demographic information be available at test time? Do we care how drastic the intervention is? And does accuracy retention matter? In other words, we're probably asking, what is fairness? in the first place before we can decide what strategy is the right one. And this is what paper 3 is concerned with, the long arc of fairness, published in fact this year. So there's a really big body of literature out there on fairness metrics. And our paper tries to organize the chaos a little bit, mainly by using the theory of justice by political philosopher John Rawls. In this case study, we've really only used 2 fairness metrics, demographic parity and equality of opportunity, without much motivation. They're grouped together here because they both look at the outcomes rather than the process itself. But we really didn't talk about this very much, and unfortunately, this is pretty much common practice in FAML research. So it's a very standard thing to do, to kind of just pick some metrics with some heuristics and then develop new technical concepts from here. Or even worse, it sometimes seems that people are trying to solve ethical problems with technical tools. So this is what paper 3 looks at. We identified 2 main problems with the literature. First, the ethical and formalized debates are conflated. Their relationship isn't clear and useful. And second, there's a lack of temporal context. We then introduce a framework that we call dynamical fairness modeling to try and fix those problems. I think the first problem is probably already clear from the previous slide, but I just wanted to explain the second problem a little bit more. So existing fairness metrics, they usually evaluate individual decisions in isolation. And I think this is for good reasons and kind of organically grown from the way we do ML in the lab. Someone shares the world, someone collects data, they hand you the data set, you train the algorithm and done. Maybe you evaluate whether the decision is ethical or not. On the other hand, I think if we think about fairness in the world, say in politics, we actually have this different idea. There's some injustice in the world, maybe some demographic groups are historically disadvantaged, and we try to design interventions such that this changes. So while you certainly can evaluate whether some decisions are fair in themselves, what you're often more interested in is whether the consequences of a decision are desirable. So a good fairness intervention is probably one that changes things for the better. We call this the interventional perspective on fairness, and it could be incorporated into modeling efforts like so. We essentially suggest to try and model some sort of feedback loop from the decision back to the world, because of course the decisions I make algorithmically, they're going to impact the world, hopefully, if they're important, and then that's going to impact the data I collect, the updated algorithm, and so on. So introduce some sort of dynamical system way of thinking about it, if you like. So let's recap here. We've identified these 2 problems: the relation between the ethical and the mathematical debates, unclear, and then the lack of temporal context. And we then try to come up with a better approach, one that we call dynamical fairness modeling. Let me just say that this work is more ethics of technology than technical work. So this is not some sort of metric or model. This is more like a framework on how we could think about modeling or how we could arrive at modeling strategies. It comes in 3 steps. First, we ask the decision maker to explicate their ethical goals. Secondly, they should formalize them mathematically. And then lastly, they should try to think of a model of the downstream effects of their decisions. In the paper, we have this case study on EU legislation regarding gender equality in the workplace. Here we replaced it with the Lab A case study from before. So let me just reiterate that automated reasoning about beauty standards can definitely be problematic. We made the choice partly because of the availability of data sets, but I also do think it's illustrative. So let's set the stage a little bit. We had this kind of employer, maybe some fashion company that's trying to automatically screen applicants. So here, whether they are beautiful or not. Maybe they're concerned with ethics, or maybe there's some sort of government body trying to set regulations for such players. The fashion company or the government, they should first, according to our modeling strategy, ask themselves, what the ethical goals are. Those would be something like diversity and inclusivity. There's also an equal opportunity and social mobility aspect to it, because one can show that whether you comply with beauty standards has actually large impact on your socioeconomic status. And then there's also this kind of damage control aspect to it, because research suggests that some beauty standards can lead to an increase in eating disorders, which are a big cost to public health. For formalizations, well, we would somehow like to formalize this idea of having a more diverse beauty standard. And what we demonstrate in the paper is how we can kind of evaluate existing methods against this ethical goals to see whether they can actually help us. So as an example, equality of opportunity here is actually not going to be helpful, because it's this, you're asking whether your predictions match the ground truth, but we're trying to change the ground truth in the first place here, right? So not probably not usable. Similar for fairness by unawareness, that just means we don't use the protected attribute directly in the decision. So here we cannot use the age directly when we make the decision, but we probably wouldn't do that anyways if we're just looking at an image or some sort of latent information. But demographic parity in the long term could work. Thirdly, we asked the decision makers to modeling downstream effects for their interventions. Here, again, we're kind of looking to measure cultural change, which is really hard. We could probably look to some work from social science, like measurement theory. Here, the work by Jacobs and others tries to bring that work a little bit into machine learning, computational sciences to use some of their concepts. If I had to come up with a proxy myself, I would probably say we could look at the change in the pool of applicants, because probably people only apply if they feel like they have a chance, if they somehow already comply with these standards. Maybe that could be one proxy. So in conclusion, we have applied the framework now to the case study to illustrate how one could potentially pick a useful fairness metric. We think dynamical fairness modeling fosters transparency. It forces the decision makers to explicate their ethical goals. And by doing so, it bridges the gap between the ethical and the technical discourse. Limitations, constructing models of downstream effects, I think is really difficult. And then a certain broad decision-making scope is required. As the committee writes in their analysis, it's not always clear how this should inform the design of individual prediction algorithms, and I very much agree with that analysis. We believe, though, that it's very much due to the nature of the problem. So it would be nice if we could just code up some algorithm to make ethical problems go away, but it's not in general possible, it seems, and these big problems, they need to be studied by a broader group of stakeholders. So we hope that we have made a contribution, at least enabling the dialogue between technical and non-technical stakeholders. So in other words, the need for context and broad scope, we think, is a feature, not a bug. Yeah, in conclusion, what have we talked about? We talked about this problem that data bias leads to model bias, garbage in, garbage out. We then investigate whether synthetic data can be used to alleviate such biases. In this chapter, we've seen that learning data augmentation is non-trivial. The naive max likelihood approach is insufficient. That's why we've looked at it in the Bayesian model selection framework, and then we have, as an alternative, looked at pose normalization for invariance learning. We have then asked whether our synthetic data can actually be useful for fairness, whether it can debias CELAB-A. We did have success, but we were wondering, how does it compare to other methods? And to answer this question, we had to take a closer look at fairness modeling in itself. The main takeaway here, I would say, is that solving ethical problems by technical means alone is pretty much impossible. We need to consider ethical goals and downstream effects. And in conclusion, I would say that despite of these limitations that we have seen in the real world, data augmentation for bias correction can be one useful tool in the fairness toolbox that should be applied like all other methods with sufficient consideration for ethical goals and context. Thanks.